Okay, the last third of this exam. Let's see if we can get to the end here. They give us three reactions here, and for each of them, they tell you how much energy is involved in it. In a couple of them, they give you the delta H's. In a couple others, they indirectly give you the delta H. They write it in line here. And they're asking us to do a calculation about the energy per mole of carbon dioxide, the molar enthalpy per mole of carbon dioxide. So because we're going to be doing that over and over again, I want to get these delta H's all written in the same format. I'm going to write all of these like these two are. This is endothermic because the energy is on the left, so it's delta H is plus 90.1. For this one, the delta H is on the right, or the energy is on the right, so the delta H is negative. And so this should be negative 41.2. And now they want the molar enthalpy per mole of carbon dioxide. For this one, there's 1 mole of carbon dioxide, so we do 90.1 divided by 1, which is a little boring. It's plus 90.1. For this one, again, there's 1 mole of carbon dioxide, so minus 41.2 divided by 1. You probably saw that coming. 514.1 negative divided by 2 moles of carbon dioxide gives us minus 257.1 kilojoules per mole of CO2. And for the last one, we divide by 3 and we get 124.7. Yeah, minus 124.7 kilojoules per mole of carbon dioxide. Fair enough? So now they want us to list these from the one that absorbs the most, which would be the most positive number, down to the one that releases the most energy, which would be the most negative number. The most absorby, the only absorby one is reaction 1. After that, the most positive or the least negative one, the highest one, is reaction 2. Then that's the highest one we have left. And finally this one. Okay, the enthalpy for the reaction shown above. Okay, well we've done this before, right? How do you find the delta H for a reaction? Say it with me. Products minus reactants. Now, before we dig in, is this thing balanced? 1 lead, 1 oxygen. Or no, sorry, 2 oxygen total on the left, 2 oxygen, 1 carbon, 1 carbon. So yeah, the balancing is okay. For products, we have lead metal, which has a delta H of 0 because lead is normally that way. And the other product is carbon dioxide, 393.5 minus. For reactants, we have lead oxide. Hope that's in our data book. Lead 2 oxide, yep, minus 219. And the other reactant is carbon monoxide. Carbon monoxide is minus 110.5, according to my book. So add those up, minus 393.5 minus, add these up and you get minus 329.5. The negatives cancel. And 393.5 negative plus 329.5. I get minus 64 kilojoules. Use the following to answer the next question. Okay, so we've seen this information before. They give us a bunch of reactions with delta H's. They give us an energy diagram that we may or may not need. The equations that represent reactions that could be represented by the potential energy diagram above. Okay, so this diagram shows us starting at low energy, absorbing energy, and then ending up somewhere higher, meaning This is an endothermic reaction. It starts low, soaks up energy, and goes high. So they're saying, which of these reactions up here are endothermic? Well, this one's got energy on the left, so that's a yes. This releases energy. That's a nope. That's exothermic. This has a negative delta H, which means it's exo, so nope. And this has a positive delta H, which means it's endo, so yep. So 1 and 4. Hydrogen cyanide is a poisonous gas used in the manufacture of dyes and explosives. The production of hydrogen cyanide is represented by the following equation. Okay, so you can take methane and mix it with ammonia and put in some heat, and you'll get hydrogen cyanide and hydrogen gas. So now you have a poisonous gas and flammable explosive hydrogen in a container that you're putting heat into, and yeah, good luck with that. The reaction represented above is, they want endo or exothermic. Well, I thought we were going to do products and reactants, but they're lovely and they did this for us already. This reaction is endothermic because the heat is on the left. So goodbye A and B. You say it's exothermic, you are wrong. And the mass of HCN produced when 1,000 kilojoules of energy is transferred would be, well, is this thing balanced? 1 carbon, 4 hydrogen plus 3 more is 7 hydrogen. We have 6 here, plus 1 is 7. And nitrogen, we have 1 on each side. So yeah, the balancing's okay. If they give us this energy, we have one formula that deals with the energy in a reaction, and it's E equals N delta H. So they're saying our total amount of energy is 1,000 kilojoules. Number of moles, no idea. And our delta H, if they want us to do HCN, it would be 255.6 kilojoules divided by 1 mole of HCN. All right, it's nice that this is 1. That means if I had forgotten to divide by 1, I would have gotten away with it. But I just want to remind you, whenever you're doing a delta H, it should be kilojoules divided by how many moles there are. In this case, it happens to be 1 mole. And why did I pick this chemical? Because they're talking about the mass of HCN, so that's the one we have to work around. So 1,000 equals 255.6 N. Divide both sides by 255. And you get 3.912. 3.912 moles of HCN. But they don't want the moles of HCN, they want the mass of HCN. So the mass of anything equals its number of moles times its molar mass. We have the number of moles. And the molar mass for HCN would be what? 1.01 for the hydrogen, 12.01 for the carbon, 14.01 for the nitrogen, 2703. That is our molar mass. 3.912 times 27.03 is 105.74136 grams of HCN. So clearly this is the closest answer. Also clearly I'm a little low. If this were 7.5 or something, then I'd round right. But as it is, the answer I got here rounds to 105.7. I take it that means I rounded a little too much here. I should have carried another decimal place or two as I was doing this number of moles. And if I had, I bet you this would come out to 105.75 or 6. And then this would round the right way. So apologies for that. I trimmed this number a little too hard. But it seems pretty clear that they want us to find C. D is not even close. Okay, energy diagram, we've seen this. Starts low, goes high. Is it endo or exo? If it goes up like that, there must be energy coming in from the surroundings, and in sounds like into, sounds like endo. This is an endothermic reaction. The reaction represented above is an endothermic reaction. There go two of our answers already. And if the energy was included as an energy term, it would be when you write the energy in an endothermic reaction, where do you put it? Should be on the left, right? Because heat is something else you have to put into the reaction to make it go. It's like heat plus raw eggs plus cheese makes omelet. Heat is one of the requirements. It's something you have to provide to make the reaction go. So heat is a reactant. It's endothermic. C is looking good. Under certain conditions, cetane can be reacted with oxygen to produce carbon dioxide and hydrogen. Okay. Did not know that, but this starts out looking like a combustion where you take cetane and burn it and you get carbon dioxide and steam. But they're saying here instead of steam, you just get plain old hydrogen gas. So this is not a combustion, it's something else. It's a decomposition or a dehydrogenation of cetane. And they give us its delta H in line. And they say what mass of cetane would be required to release 1 gigajoule of energy? Well, we have a formula that can do stuff like this. Total energy equals N delta H. The total energy is 1 gigajoule, which is 1 times 10 to the 6 kilojoules. There's 1,000 kilojoules in a megajoule, and there's 1,000 of those in a gigajoule. So 1,000 kilojoules is what it takes to make a gigajoule. There's a few other ways to convert that, but there's one way, and you can talk to your instructor if you would like to see more. That's our total energy. Number of moles, don't know. Delta H, well, it's 11,456 kilojoules for every, hooray, it's 1 mole of cetane. The fact that it's 1 means I don't actually have to divide this. The number's not going to change. So I have 1 times 10 to the 6 kilojoules equals N times 11,456 kilojoules per mole. For the numbers, I didn't need to do anything, but kJ over moles is still there. And now, if we want to solve this for N, we divide both sides by 11,456. I put in a million instead of 1 times 10 to the 6 because I avoid scientific notation when I can. And when we divide that out, we get our number of moles is 87.29050279 moles of cetane. I just did a question where I rounded off a little bit too much, so now you get to see me go insane and carry way too many decimal places for the next few questions because I'll not want to repeat that mistake. So that's our number of moles, good, but they want a mass. And the mass for something is its number of moles times its molar mass. Number of moles is that 87 thing I just found. 290500279 times, and the molar mass for cetane will be 16 times 12.01 plus 34 hydrogens is 34.34 because hydrogen's nice that way. Molar mass for cetane is 226.5. Multiply that by 87.29050279, and I get 19771.29888 grams of cetane. Okay, that's clearly way too many numbers. How much do we actually give? This has 3 sig digs. This has 5 sig digs. 3 is definitely our worst measurement here, so we have to cut this down to 3 sig digs. We could divide by 1,000 and say 19.8 kilograms of cetane, or we could go to scientific notation and say 1.98 times 10 to the 1, 2, 3, 4 grams of cetane. Either one of those would be fair. Bombardier Beetle can release a chemical solution when threatened. Glands in the beetle produce peroxide and hydroquinone, which are combined to produce the reaction represented by the overall equation below. So, Bombardier Beetle it almost looks like a spray bottle. They release chemicals from two separate glands right up by their horns. When those chemicals mix, they produce so much heat that the mixture almost boils, and it bursts out from the front of their head. I believe it's hot, and it makes kind of a snapping or popping noise because of the sudden reaction, and it's scary, and it makes you want to go away and not eat the beetle. So the reaction is hydroquinone reacts with hydrogen peroxide, and it produces C6H4O2. I can't tell off the top of my head what that is, and water. And here are some other reactions. And you can see what's coming. This is going to be Hess's law. We're going to have to take these reactions in some combination to build this thing up and then find its delta H, because that's what Hess's law is for. So let's see. Our finished reaction must contain hydroquinone, and the only place we could possibly get it is equation 1. So we have to write equation 1. It's already 1 mole, so we don't want to change the number, and we don't need to flip it at all. So I'm just going to say reaction 1, unchanged. That gives us C6H4. In other words, I'm just recopying this thing. OH2, C6H4O2, and hydrogen. Okay. We must also get hydrogen peroxide. We need 1 mole of that on our left side. We've already used reaction 1, so we don't want to revisit that. This, reaction 2, is the only one that could give us peroxide. Unfortunately, it's on the right side here, so we must flip this reaction. So I'm going to say minus reaction 2. Whoops. We'll keep it Roman numerals like they're using. Minus reaction 2 means reaction 2 flipped. So we flip this, we get H2O2 on the left. Arrow. On the right, we get H2 and O2. I'm not doing the delta H's yet. I'm sure you've noticed. I'll get to those once we've got our reaction squared away. Okay, what else? We need C6H4O2 on the right side. We already have that, so great. And we need 2 H2O liquid on the right. We can get that from this reaction. If we write 4 as is, that'll give us H2O liquid on the left. So we get H2O gas on our left side. We get H2O liquid on our right side. Okay, so that's good. Now here's the problem. If we add this up, let's see what we've got here that we want to keep and see if there's any problems. And spoiler alert, there's a problem. We have C6H4OH2. We want that. That's this. We need a peroxide on the left, and we have it, so that's nice. We need a C6H4O2 on the right, and there it is. Oops, we need 2 liquid water on the right, don't we? Instead of just reaction 4, we should have done 2 times reaction 4. That'll give us twice as much water here, or twice as much steam on the left, twice as much water on the right. Okay, so that's good. But now here's the problem. We have this liquid water that snuck into our reaction, and we don't want this. We must cancel it out. Happily, we have reaction 3 that will do exactly that. If we put 2 H2O gas on the right, it'll cancel these guys. We can accomplish that by doing 2 times reaction 3. That'll give us 2 H2s. And 1 O2. And I just noticed the hydrogen isn't matching up. I'm afraid I may have miscopied something up here, and we'll follow up on that in a moment. We're doubling reaction 3, so 2 H2s, a single O2, and that'll give us 2 H2O gas on the right. Okay, so that's good. These H2Os cancel out, which we wanted. Now, the thing is, I thought the hydrogen would cancel also. The oxygens cancel, and that's nice. The hydrogens do not cancel, and I'm hoping that's just a copying error. If I flip reaction 2, no, that should be 1 H2 and 1 O2, so that's legit. Reaction 3, if you double it, you should get 2 H2. Ah, I see, here it is. I missed this. There are 2 hydrogens on the right. See that? Here's 2 H2s. Those will cancel against that hydrogen and that hydrogen, so it did all work out. Good. So everything cancels except 4 species we want. That tells us that these reactions are okay. And now we have to find our delta H. So, big finish. What did we use for reactions? We used reaction 1 unchanged, which means we get reaction 1's delta H unchanged, plus 177.4. 177.4. Minus reaction 2 means we get minus this delta H, so plus 191.2. 2 times reaction 4 means we get 2 times this delta H. So double that and you get minus 87.6. And 2 times reaction 3 means we get 2 times this delta H, so minus 483.6. $177.4 plus 191.2 minus 87.6 minus 483.6 minus 202.6 kilojoules. That's one of those answers, so hooray, looks like we made it. And last one, hydrogen sulfide undergoes combustion as represented by the following unbalanced equation. This is not a hydrocarbon like we're used to seeing, so we call this a combustion, but it's not a hydrocarbon combustion. It's a little bit different. It still reacts with water. It still produces steam, but it produces sulfur dioxide instead of carbon dioxide. And they tell us the delta H was this much. But then the question is just, what are the number of moles for each of these things? So I guess they just want us to balance this? Okay. Can do. 1 sulfur, 1 sulfur. Fine. I'm still doing oxygen last just because that's a habit I picked up from hydrocarbon combustions and I trust it will still work here. So I did sulfur first because I normally do carbon first, and I'm hoping that that pattern still holds up where you do the H and O, you do H second and O last. So sulfur, 1 and 1, good. Hydrogen, 2 and 2, good. Oxygen, we've got 1 there plus 2 there, total of 3. So here, you could write 1.5. Okay, so one way to balance this would be to say that's 1, that's 1.5, that's 1, and that's 1. The trouble is, this is a numeric response question. Or no, it's a type of number in the box question. I feel like they aren't expecting this fractional answer. And if you write 1.511, it may look a little weird and it's probably not what they're looking for. So if we wanted to get rid of that fraction, what do? Double the whole thing. You can say twice as much H2S, twice as much oxygen, twice as much steam, twice as much SO2, and now we have a nice neat answer, 2322. So I would advise you to give something like that. If you put 1.511, if a human's marking that, they're going to understand what you did and you'll probably get the point. But I'll bet you the machine would choke if you gave it this. So definitely a better plan, less drama if you go with that one.